In the following series of lectures, we're going to be talking about special structures in problems, how we can identify these structures in problems, and how we can use these structures to actually solve these problems in an efficient way. The first structure we're going to talk about is non-decreasing submodular functions. These functions are going to be set functions. That is, these functions map every set that's a subset of a superset n to a real number. And this function is going to have two properties. It's going to be non-decreasing. That is, if we look at two sets A and B, and A is a subset of B, the function evaluated at the smaller set is a lower value than the function evaluated at the larger set. The function is also going to be submodular. That is, if we have two sets A and B, the function evaluated at A plus the function evaluated at B is going to be greater than the function evaluated at the intersection of these two sets plus the function evaluated at the union of these two sets. We're going to give an idea of what submodularity actually means. Non-decreasing should be pretty straightforward. Larger sets get larger values. Here we have an example of a non-decreasing submodular set function. The set that we're defining our sets on is a superset n. These are black points. And we can verify that among the sets shown, S1, S2, and S3, that the non-decreasing property holds. That is, S1 is a subset of S3, and it has a lower function value. Similarly, S2 is a subset of S3, and so it has a lower function value. We'd also like to verify the submodularity property. In this case, we'll verify the submodularity property for S1 and S2. So we can start writing that f of S1 plus f of S2 is greater than or equal to f of S1 intersect S2 plus f of S1 union S2. Now we can verify these particular values. F of S1 is equal to 2. F of S2 is also equal to 2. F of S1 intersect S2 is the empty set, and that has a value of 0. F of S1 union S2 is S3, so this value is 4. And we can see that this is met with equality. In addition to verifying that this is submodular, we can also talk about what exactly submodularity doesn't say. We can, for example, have another set, let's say S4, and evaluate this function value at S4, and it can be pretty much anything we want. Submodularity with respect to S1 and S2 doesn't say anything about this set S4. When we have a set function given to us, it's easy to verify whether it's submodular or not, but it's better to have an idea of what submodularity is trying to say. Here we're going to do that. The idea behind submodularity is that we have diminishing returns. And it's best to understand this when we have two sets A and B that are disjoint from one another. Here we have two sets A and B, and they're disjoint from one another. What submodularity says is that if we evaluate the function at A and add the function evaluated at B, that's going to be greater than evaluating the function at A and B together. That is, when we pool A and B, we somehow get a diminishing return by pooling A and B together. The specific idea behind submodularity is that we can handle both sets that are disjoint and sets that aren't disjoint. In this case, we have two sets A and B, but they have a little bit of overlap. We'd like to have this idea of diminishing returns, and so what we do is we look at A union B, and somehow say that this is going to be less than evaluating A and B together. But we have to have a particular correction term. We have to have A intersect B, and this is going to correct for double counting. The idea here is that when we evaluate the set function at A and B together, we evaluate A, we evaluate B, but we also double count in spaces where we have A and B overlap. So to account for this inside of our diminishing returns idea, we have to include a term that corrects for this double counting. And that's exactly what A intersect B does. In addition to the original definition of submodularity, we can use another equivalent definition. This equivalent definition looks at two sets, A and B, and some element that's not in either A or B. Now we look at the function evaluated at A and E together and subtract out the function evaluated at A. On this side, what we're really evaluating is the additional amount of value we get by adding E to the set A. On the other side, we see a similar thing, but now we're looking at the additional value we get by adding E to the set B. Submodularity tells us that if we add E to the smaller set A, that we get more value than adding E to the larger set B. In this way, we look at the submodularity as having diminishing positive returns. That is, we add an element and we get a positive return, but it diminishes as our set gets larger. Submodular functions are generally very simple, but sometimes they can become quite complicated. We're going to look at a particular example of a submodular function that is a little bit complicated. It's not trivially simple. The idea is that we're going to have a set of facilities and a set of clients. The facilities will be indexed by J and the clients will be indexed by I. We're going to look for the service level for the client I from facility J. And what we'd like to do is intuitively look at a particular set, and inside of this set, we're going to select all of the facilities, and every client is going to go to the facility that serves them best, that is, gives them the highest service level. Here we've written down that function. F of S, for some S that's a subset of our facilities, is going to look at every particular client, and every client is going to look at the facility that we've picked that gives them the highest service level. We're going to drop some of this notation so that we can explain it a little bit easier without having all of these brackets and sets. We can prove that this function is submodular. To prove this is submodular, we use the first definition. And generally, this is the definition we're going to use when proving a function is submodular. The way we go about it is first writing one side of that equation, that is, the function evaluated at A plus the function evaluated at B, which we've written here. Then we expand out what exactly this function is. After we expand out what this function is, we have to do some intuitive analysis and no longer write equations. This intuitive analysis is going to look client by client. And for each client, it's going to compare the service level this client receives in facilities in A to the service level it achieves from facilities in the set B. The first case we consider is the hardest case. In this case, when a client considers the facilities in A, the highest service level is achieved by a facility in A and not in B. Conversely, when they consider facilities in B, the highest service level they achieve is from a facility in B that's not in A. When they look at facilities in the intersection of A and B, it has to be some third facility, and this third facility is going to achieve a strictly lower service level than either A or B. Now we can compare this in terms of the inequality we need for submodularity. The client receives some service level for sets in A, and some service level for sets in B. We've identified both of them. The service level it achieves in the intersection of A and B is something strictly lower than either of these. The service level they achieve in A union B is going to be the max of A and B. And so for this particular client, this inequality is going to hold. This is ignoring all of the sums over I. This is in some sense the hardest case to consider. In another case, we have when clients consider facilities in A, they choose some facility of highest service level, and it's in both A and B. When they consider just the set B, there's some facility that achieves the highest service level that's in B but not A. Note that this facility that's in B but not A has a strictly higher service level than the facility that's in both A and B. That's because this facility that's in both A and B, being in B, has to be dominated by the one that's strictly better than it, this pink guy. Now when we consider the inequality, we have the service level achieved in A and the service level achieved in B, these 2 points. Now when we look at A intersect B, the best facility for this client is going to be this blue guy. And when we consider A union B, the best facility is going to be this B guy, because we know that this one dominates all of the other elements in A. In this case, the inequality is actually met with equality for this client. The next case is rather similar and symmetric, so we won't go through it. The final case is when a client considers facilities in A, they choose some facility that's in both A and B. Similarly for B. Now when we look at this equality, we see that when the clients consider all the elements in A, they consider this one facility. When they consider all the facilities in B, they consider again this one facility. And also when they consider anything in the A union B or A intersect B, they also consider only this facility. This facility is the one that dominates, and so this inequality is again met with equality. Since this inequality is true for every client, it's going to be true when we sum over all of the clients. And recall, the way that we now analyze this is a very intuitive analysis based on the different cases. Finally, what we write is that the function evaluated at A plus the function evaluated at B is greater than or equal to the function evaluated at the intersection of A and B plus the function evaluated at A union B. This proves that this function is submodular. We'd also like to show that this function is non-decreasing. This is fairly straightforward. If we have some set A, then the client has less facilities to consider than if we have some set B. So the service level achieved by all of the facilities in B for any individual client is going to be greater when we look at the set B, because there's just more for the client to choose from. So this function is non-decreasing.